I'm sure everyone knows of extreme forces created by fictional characters, blowing up planets, stars, galaxies, and even entire universes. Now, these obviously aren't physically realistic, but it begs the question, by how much? What would such extreme forces really look like if they were to actually happen in real world physics? Or at least something approximately like it. Before we start with this, we will start with the theoretically highest force that still works within modern physics, the Planck Force. To explain this, the Planck units are essentially normalizing units that use only the speed of light, the gravitational constant, and Planck's constant. Beyond being just simply an exercise of mathematical reasoning, it also had the possibility of simpler mathematics for future equations, as is the case with other natural units such as geometrized units. These units have also been found to coincide with both quantum effects and gravity becoming significant, making traditional theories simply fall apart, as no one knows how these two things will interact. Using the method devised by Planck, we can create a force of units, which becomes the fraction of the speed of light to the fourth power divided by the gravitational constant. Obviously, this is a very large number. In SI units or newtons, it is roughly 2 times 10 to the power of 44 newtons. Many have conjectured that this is the largest force that can occur. Others dispute this idea. Even some have found that in traditional general relativity, there is a number simply 1/4 of the Planck force that is so strong that it'll create a black hole just from acting upon pretty much anything. Though, until the theory of quantum gravity has been resolved, no one truly knows the answer to this question. Being as we obviously don't have a theory of quantum gravity, no one really knows what will happen with a Planck force. But focusing just on general relativity should be a guess that at least has some fun involved, if not some aspects of truth. Here I'm going to use Einstein's toolkit, a very helpful open source numerical general relativistic codebase. In addition, I will create a thorn, or my own personal code, to strike an object with a force. Then I edit the neutron star TOV simulation, which is a static star in flat space-time, to make it somewhat like Earth. It's obviously not super close, but in such an extreme case, I doubt it'll make much of a difference. Doing this was surprisingly difficult. I thought it'd be the easiest part, but I was wrong. After running it, I got this data below. While you likely can't read the numbers, and they are strange units at that, so I'll simply explain. Very quickly, the contact explodes into a vacuum at relativistic speeds. Then, as the relativistic speeds add up, it creates mass that slowly creates such a strong gravity that it overcomes even this intense pressure wave, collapsing into a small point, a point roughly the size of a single mesh in this simulation. Thus, including things like the fusing of particles through nuclear fusion, neutron degenerate matter, or even the collapse of a black hole would require much more advanced simulations. There is also another bigger problem. The force being added is so great that it causes the particles to reach superluminal speeds before the next time step, leading to the simulation coming to an error as mass becomes imaginary as the Lorentz factor goes to infinity. The creators of this toolkit obviously came up with a solution. I'm not 100% sure what their solution is. It simply says an error that something has been reset, so I don't actually know the accuracy of the simulation, and the knowledge of what is actually going on is beyond mine. I try to decrease computational complexity and decrease the time step substantially. I made the simulation symmetric, so I only had to simulate 1/8 of the Earth, 2-dimensional rather than 3D, and increase the size of the mesh. I eventually got a single time step to be 1/10 trillionth of a second. Still, I got the same warning, so I had to accept the fact that I simply wouldn't know. I would think that it would collapse into something, but not into a black hole, like a mini star that would eventually over time explode out. But this is not something that I can confirm. To do so would require something much more than my own personal computer and messing with Einstein's toolkit. Now, while that simulation was rather disappointing, there's still the question about exploding the universe, which is surprisingly much simpler. To do the simulation, we will first need to make our assumptions about said universe to simplify the simulation. 1. We will assume that the current observable universe, 93 billion light years in diameter, is the size we'll use. Assume that matter outside such volume would have a negligible effect on our simulation. 2. We will assume that space-time is mostly flat. Most observations put the universe at extremely small overall curvature, but that small change likely won't change the results of the simulation by an order of magnitude, which is where we're trying to go towards, not towards the exact number. 3. We will take dark energy to be constant, such as through the vacuum energy model. While recent studies dispute this idea, they have trouble coming up with an exact value, so for now I will leave it in the simplified model. 4. With dark matter, dark energy, and with regular matter, we will use estimates of value of both Hubble's estimate of dark matter and Schu's as well. 5. We will take a relatively isotropic density of the universe, meaning a relatively constant one rather than variable. 6. When we later talk about the energy of the force, assume that it is some kind of magic or from another universe that is being created or added to the universe when it simply wasn't there. Obviously, this isn't physically realistic, but neither is what we are trying to accomplish. Now we have an actual model of the universe. Being filled with so much empty space, it is pretty obvious that you can't punch something and blow it up. If you punch anything, everything would turn into superheated plasma, possibly even breaking into quark gluon plasma, which these things might hit a couple of surrounding areas, but likely wouldn't be able to destroy anything no matter how hard the explosion was. So it's pretty useless. We'll take another solution. In a previous simulation, the Earth collapsed from gravity, so it is conceivable that an intense enough force could theoretically collapse into a black hole. So now, first, we'll work backwards. To get the force, we need to take energy, and to get the energy, we can find the analogous mass needed to overcome gravity. We start with FRW Friedmann equation. Here we will compress the parentheses into EA for simplification. Next, we take source-child de Sitter metric function for a relatively flat expanding spacetime. Here, one can take the derivative and find that the derivative is equal to 0 to find the point in which the universe becomes static. Then solving for mass, when the radius is the current size of the universe, we get the equation below. And for an exact solution, we get the next equation. Here we can take the Lemaitre-Tolman-Bondi metric, an exact solution to Einstein's equation for a lump of matter with no assumed symmetry. Here we can see that the structure of the shell makes no difference, only the total mass in it. From here, simple algebra allows us to find the energy needed to lead to the eventual collapse, and the function to solve it when it crosses 0. To actually solve it, we'll use the values for Hubble constant, mass and energy of the universe, and some others. Since there is no exact values for these, we will use a Monte Carlo simulation to show Bayes' uncertainty about the true values. From here, we simply run the simulation, getting the results below, with the total energy needed to overcome the gravitational binding energy of the universe. As we mentioned earlier, the purpose of this isn't simply to find the energy, but rather the force. I know some people watching this will likely know the general work formula. force times distance equals energy. But in the case of relativity, it doesn't always work. Though with a couple of simplifications, we will end up with a very simple formula quite analogous to it. Let's assume a practically flat spacetime to make the calculation simple. From here, the fact of conservation of energy momentum makes it so the stress energy tensor, which is both energy momentum is clear, derived to be the general derivative of the stress energy tensor is equivalent to the 4-force, essentially Einstein's equivalent to Newton's force. Here we can expand it to this longer equation, where we can find that the first term is simply the energy added to the force by volume, and the other three terms simplify to this equation below. To simplify the calculations, we will focus simply on the energy density portion, or the first term. The result would be the same, just differing math, so we'll move on from there, as adding that would cause significant complexity. So if we take the median value of the energy from our earlier simulation, 3.6 times 10 to the power of 71, this force spread out through the volume of 1 meter, the energy density is equivalent to the force, and thus would be 3.6 times 10 to the power of 71 newtons. As I've mentioned, this is an extreme simplification, but working with such high orders of magnitude, there's really no physical object that would lead to initial energy or pressure gradient or any of such things to have a non-negligible effect on it. So we have a force, 36 followed by 70 zeros. That's about 67 orders of magnitude beyond the average punch of 1,000 newtons. 66 orders of magnitude over the highest ever recorded punch at 69,000 newtons. For comparison, that is 25 orders of magnitude above the estimated energy released in the Big Bang. On the order of comics that we've mentioned earlier, I had to find some feats that could have real numbers, not estimates based on the wacky comic book physics. So I chose Superman pulling a chain of planets very, very quickly. With this, other people estimate it to come somewhere between 10 to the 38th to 10 to the 40th newtons. Still on the upper end, being 31 orders of magnitude away. Humans are closer to Superman's feat than Superman is to this calculated feat. Now I'm sure there are a couple questions that I can anticipate. If gravity moves at the speed of light, how would this change things? The answer is not a sane amount. Redshifting and losing energy is only for waves, so a constant gravity would not lose energy. Our model makes sure gravity overcomes dark energy by definition. The main change would be the change in the radius of the universe, and the fact that parts of the universe that are currently observable would move past the cosmic horizon, where gravity would never reach it. These two aspects counteract each other by increasing the radius but decreasing the mass of the universe. And since we're working with such large numbers, these small changes that both counteract each other probably won't change many things. Obviously, I could be wrong, but this is what I have found. Thank you for watching.